Hello, everyone.
Awesome.
How are you guys doing today?
Good.
Good. How are you?
I'm doing fine. Thank you for asking. So, we are going to have a fun class, I hope. We finished 1.4, and today we're going to start 1.5. And then we have, I think, 1.6, do we? Let me see. 1 point. Oh, no, 1.5. Cool. After 1.5, we'll be done with chapter 1. So we are going to go chapter 2 after that. But 1.5 is a little bit longer, so probably it will take us 2 to 3 lectures. Any question before we start? Any comments, concern, complaint, anything? Nothing?
I have a question. Are we behind on lessons?
Not really. I'm going slower, but we're fine. I know the instructors, they are way ahead of us, right? Did you hear anything from any?
Yeah, because I have a friend in Matrix as well, and he's doing chapter 2 right now. I just wanted to know.
Yeah, I know. But I told this was before, so I know my pace. We'll be fine. So, elementary matrices, section 1.5. So, last time we saw that we did reduced row echelon form to solve matrices, but now we don't have to do reduced row echelon form. There's also another method by which we can solve for matrices, and that another method is called using elementary matrices. So if you have a system of equations, X equals B as an equation format, then in order to get the X alone, means the variable matrix alone, we can multiply both sides by A inverse, or we can do something, we can multiply by other matrices, and then eventually the A matrix will turn into A matrix will disappear. Yep. So this process needs elementary matrices. So what elementary matrices are? It's a matrix that is only one step away from being identity matrix. So a square matrix is an elementary matrix where it can be obtained from the identity matrix by a single elementary row operation. So the elementary matrix is very, very, very close to the identity matrix. The difference between elementary and identity matrices is that you can apply only one row operation on elementary matrix, and then it will turn into identity matrix. If you need to apply 2 row operation, that means it's not an elementary matrix. Elementary matrix requires only 1 row operation. So in short, if you start with an identity matrix and then perform exactly 1 elementary row operation, then the resulting matrix is the elementary matrix. So you can go from one way to another, like identity to elementary or elementary to identity. They are very closely related. And then what row operations are talking about here? That's allowed. First of all, that row operations we're allowed to use in performing row echelon form. We can use, these are the 3 allowed operation. Say here, First one is we can interchange two rows. We can swap them, or we can multiply a row by a non-zero constant. We cannot multiply by 0. And then we can multiply one row by a non-zero constant and add with another row. In other words, we can add two rows, we can multiply by a non-zero constant, and we can swap two rows. These are the three allowed operations we can apply on IIT matrix, and we can get elementary matrix. For example, the first example here, we have a matrix row-wise 0, 1, 0, 1, 0, 0, and 0, 0, 1. Now, if you compare this with the identity matrix, we know that identity matrix is 1, 0, 0, 0, 1, 0, and 0, 0, 1. This is the identity. If you compare the left one with the right one, they're almost identical. The difference is these two rows are swapped. So first row and second row is swapped. So the operation we use here is we swap row 1 with row 2, and then it becomes identity matrix. So E1 is an elementary matrix because we can apply only one row operation and it turns into identity. The second one is also an elementary matrix because if you compare E2 with the identity, the only difference is you multiplied the identity matrix by 3, the third row. Or if you divide this matrix by 3, it will turn into identity matrix. And then the last one is not visible directly, but actually it is elementary matrix because if you observe our row 1 is actually row 1 plus 3 times row 3. So you multiply row 3 by 3, you get 0, 0, 3. If you add with 1, 0, 0, the result is 1, 0, 3, which is the first row. So E3 is also elementary matrix because we applied only one row operation. Any question? Any comments so far? No? Okay, then you have a few to work on. Try this and figure out whether they are additive, whether they are elementary matrices or not. If they are, then what type of row operation was applied? And if they are not, then why not? I have 3 more on the next page. So once you're done with this, thinking about this, let me know. I'll change my slide. So we have Mahi, Brandon, Chuyan, Alvin, Emily, Shibu, Jack, Ove, Joseph, Justin, Tyrone, Kenyon, Michelle, Shafal, Shakila, Anshuan, Umtan, Zibon, Edison. Okay. Ready, guys? Let me change my slide, and we have 3 more. Think about whether there are elementary matrices or not. If yes, why? If no, why? Again, elementary matrix, since you have to compare that with identity, that means they have to be square. Because every identity matrix is a square matrix. This is I2 and this is I3. Ready? Who is ready to give me the answer for A? You just have to tell me whether A is an elementary matrix or not. If yes, why, or which row operation was used. And if not, then why not? Jack.
For A, the
Hmm?
second row was multiplied by 3.
Good. So row operation was R2 multiplied by 3. So this is yes. Perfect. Ashif.
For B, you swap row 2 and row 3.
So we swap them. So row operation was swapping row 2 and row 3. So this is also an identity matrix. So not elementary. Good job. C. Who is ready for C? Go ahead, Ashif.
You multiply row 1 by 2 and then subtract row 1 from row 2.
So row 2 is 2 row 1. Subtract or add?
Subtract, right? Yeah, subtract.
2 row 1 minus row 2.
Or row 2 minus 2 row 1.
Row 2 minus 2 row 1. Okay. Row 2 minus 2 row 1. So 2 row 1 is 2 0. Row 2 is 0 1. When you add, you get 2 1. Perfect. Yep, you got it. Okay, next page, D. We have 1 0 0, 0 1 0, 0 0 0. Who would like to try D? Come on, guys. You don't have to be correct, okay? Just tell me your ideas. Shibu.
Hello.
Yep.
I don't think this is elementary
Why not?
because there's no way in the 3-row operations that we can make 0 0 0.
Exactly. 0 0 0. We cannot get from one elementary operation. Perfect. E. E. Again, you don't have to be correct, okay? Just give me your ideas. Which one?
I don't think E is elementary because you need to use two operation.
Good. Need two operations if you want to convert it into identity matrix. Good job. Now the last one, the easy one, the easiest one. Gibran.
Hello?
Yep.
Okay,
Go ahead.
it's not a elementary matrix because it's not square.
Good job. It's not a square matrix. See? Cool. Now you know what type of matrices are elementary and what are not. So these are the solutions, and we already know them. Now there is a theorem about elementary matrix. Kenyan, question?
Yeah, with C, how many operations did we use?
C or E?
C.
C. We use only one operation. It's row 2 minus 2 row 1. So this is addition or subtraction of 2 rows with a multiple, which
Okay.
is this one. Add a multiple of a row to another one.
Okay.
Any other question from anyone? No? Okay, so one theorem about elementary matrix. If E is an elementary matrix, then E is non-singular. Non-singular means easier than inverse. And E inverse is an elementary matrix also of the same type. What does that mean? It means if E is an elementary matrix with type 1 means you're swapping two rows. If you have an elementary matrix that is obtained by swapping two rows, then E1 inverse is also an elementary matrix with the same property. You swap two rows and you get E1 inverse. Okay. If you have another elementary matrix, let's say with the third operation, multiply by a constant and then add with the other row, then E3 also has an inverse, and that inverse function has the same operation. Multiply by a constant and then add with another row. This is what this theorem is saying. The next concept is equivalent matrices. Once you know that matrix multiplication is possible without even solving anything, we can figure out we can work with the equivalent matrices. In M by N, it means it doesn't have to be strictly square matrix. Any type of linear matrix, Ax equals B, we can obtain an equivalent system by multiplying both sides of the equation by a non-singular M by N matrix. So previously we learned that we can rewrite system of equations in the form of the equation Ax equals B. And now to solve for X, we can multiply both sides by matrix M, and then we can solve for our X easily. So Ax equals B, whatever solution you get from here, you will get the same solution for MAX equals MB, because these two are equivalent matrices. Equivalent matrices means two matrices, they have the same solution. Okay. Now, when you talk about elementary matrices, so equivalent matrices, there are several types. One is row equivalent, one is column equivalent, and there is another type I forgot. But in this class, we are going to talk about only row equivalent. A matrix B is row equivalent to a matrix A if there exists a finite sequence of elementary matrices such that when you multiply A on the left side by all these matrices, they turn into B. So A and B, they will be equivalent if you can obtain, if you multiply A1, so if you multiply A by a bunch of necessary elementary matrices on the left side. So you keep multiplying on the left side, and eventually if the whole result turns into B, then A and B, they're equivalent. Now, the properties of that row equivalent matrices. If A is a row equivalent to B, so you have two matrices, A matrix and B matrix. They're row equivalent. It means they're same matrix by row when you multiply on the left side of A matrix. Or if you multiply B on the left side by elementary matrix. So B, you multiply E1, E2, E3, it turns into A. If eventually multiplying B by a bunch of elementary matrices gives you the exact A matrix, then also A and B are equivalent. So if A is equivalent to B, then B is also equivalent to A. So it works both ways, okay? And then the next one says, let's say you have A is equivalent to B and B is equivalent to another matrix C. That means the A and C, they're equivalent to one another. So A is equivalent to C. It's just like normal number multiplication. If number A equals number B, then B has to be equals A. And if A equals B and B equals C, that means A and C, they're the same thing. The same concept is true for row equivalent matrices. Now, finding the elementary matrix. Given the square matrix A, to find its elementary matrix, or a series of matrices to convert into another matrix B, write the matrix as the format A and a vertical bar I, and then convert into B, vertical line EM. What does that mean? Let's say you want to find what elementary operations you can apply on A so that you can get its row equivalent matrix B. How can you find that elementary matrix or elementary matrices, a bunch of matrices? To find that, we are going to rewrite A matrix as A vertical bar I. And then we are going to apply row operation 1, row operation 2, row operation 3, whatever is needed here. And then eventually we'll stop when this turn into B. And then whatever we have here, once you do the operation, that is our elementary matrix. Okay. So basically we write original matrix and identity matrix side by side, and we apply row operation so that we want to get what we desire to get. And this is also one of finding the inverse matrix. Do I have it here, the inverse matrix? No, later. Okay. So let me show you a good video which has good explanation of all these things. It's only 3 minutes. So let's go there. Yeah.
This linear algebra problem, it says let A be this 3x3 matrix and B be another 3x3 matrix. Find two elementary matrices E1 and
Can you just hear
E2
it?
such that E2 times E1 times A equals the matrix B. So basically this is just a problem testing if you know what elementary
If you
matrices
can
are and how to
hear,
find them. So
and
let's go over that in this
you
video.
can
So by definition, an elementary
increase the
matrix
volume.
is a matrix which differs from the identity
Let's
matrix by one single elementary row operation. So to solve a problem like this, we want to take the matrix that's being
Okay.
multiplied,
Can
which
you hear
is
it
the
now?
matrix A. Hey guys, in this video I'm going to do this linear algebra problem. It says let A be this 3x3 matrix and B be another 3x3 matrix. Find two elementary matrices E1 and E2 such that E2 times E1 times A equals the matrix B. So basically this is just a problem testing if you know what elementary matrices are and how to find them. So let's go over that in this video. So by definition, an elementary matrix is a matrix which differs from the identity matrix by one single elementary row operation. So to solve a problem like this, we want to take the matrix that's being multiplied, which is the matrix A, and then perform two elementary row operations on it to get matrix B. And we know it's 2 because we need two elementary matrices. So we want to do elementary row operation 1 and elementary row operation 2 to get the matrix B. And then from these elementary row operations, you can get the elementary matrices. So to do that, we're going to take a 3x3 identity matrix and then perform the elementary row operation 1, and that will give you E1, which is the first elementary matrix, and you do the same thing with elementary row operation 2 on a new identity matrix, and that will give you the second elementary matrix. So let's go ahead and solve the problem so you guys can see what I'm talking about. So we're going to take the matrix A, which is 1, 2, negative 1, 1, 1, 1, 1, negative 1, 0. And the first elementary row operation I did was R3 plus R1. So that gives me 1, 2, negative 1, 1, 1, 1. And then for the third row, it's 2, 2, 1, negative 1. And then the second elementary row operation I do is R2 minus 2R3, and that gives 1, 2, negative 1, negative 3, negative 1, 3, 2, 1, negative 1. And so that's A, and that is B. So to find the first elementary matrix, we're going to take a 3 by 3 identity matrix, and we're using 3 by 3 because we are given 3 by 3 matrices, so we know that the identity has to be a 3 by 3 matrix. So a 3 by 3 identity matrix looks like that, and we're going to perform the same elementary row operation that we did the first time for A. So that's R3 plus R1, and that gives 1, 0, 0, 0, 1, 0, and then 1 plus 0 is 1, 0 plus 0 is 0, and 1 plus 0 is 1. So that is equal to the first elementary matrix, and E2, we're going to do the same thing, but for the second elementary row operation, which was R2 minus 2R3, and that gives 1, 0, 0, 0, 1, negative 2, 0, 0, 1, and that's equal to the second elementary matrix. So that gives us E1 and E2 such that A pre-multiplied by E1 and then E2 is equal to B, and we're done with this problem.
Okay, ready? Any questions so far? Any question, comments? Any complaints so far? No? Okay, so you can have a bunch of elementary matrices, or you can have a sum of the bunch of elementary matrices. So if you use this method, you don't get one elementary matrix, you get the sum of all the elementary matrices. So if you want to find one individual one, then you can do that way they did in the video. So we have A and B. If you compare, when you compare A with B, we need to figure out what row operation we applied on A so that it turns into B. And we're going to apply the same row operation on the identity matrix. So we have 5 and 3 on the bottom. So our A, let me read it row wise. A matrix is 2, negative 1, 5, 3. B matrix is negative 4, 2, and 5, 3, row wise. So our second row, 5, 3 are same in both A and B. Our first row in A and B, they are different. A has first row 2, negative 1. B has first row negative 4, 2. So that means we are only comparing our row 1 in A with row 1 in B. So we need to change our row 1. What can we do in A so that it turns into B? Ashif.
Negative 2 R1.
Negative 2 R1. So we are going to apply the same thing on the identity matrix. We have 1, 0, 0, 1. And if you apply row 1 as negative 2 row 1, we get negative 2, 0, 0, 1. So this is the elementary matrix we are looking for, what they're asking us about. So if you multiply E and your A matrix, it will turn into your B matrix. So if you want to see it's true or not, you can take negative 2, 0, 0, 1 and multiply with 2, negative 1, 5, 3, just to check your work or verify your work. When you multiply, we do row and column. So you get negative 2 times negative 2 is 4 plus 0. and then -2 times -1 is +1, sorry, +2. Then 0 times 2 is 0, so 5 times 1 is 5, the second row. And then 0 times -1 is 0, 1 times 3 is 3. So we get same thing as B, -4, 2, 5, 3. So yep, the elementary matrix we got, it's correct. The next one. If you compare A with B, what do you think they did to turn A into B? So let me read the matrix first. The A matrix is 2, 1, 3 row wise, -2, 4, 5 second row, 3, 1, 4 third row. B matrix is 2, 1, 3 first row, 3, 1, 4 second row, -2, 4, 5 third row. Ashif, you raised your hand, right?
Yeah, row swap 2 and 3.
So row 2 swapped with row 3. So in the identity matrix, we have 1, 0, 0, 0, 1, 0, 0, 0, 1. If you swap these two rows, you get the elementary matrix 1, 0, 0, 0, 0, 1, 0, 1, 0. And this is what they're asking us to find. Who is lost? We have no idea what we are doing. Anybody? Please don't be shy, or don't be shy, or don't get scared of asking questions. If you don't understand anything, please let me know. I'll help you to understand the material. Any questions?
I have a
Question?
question.
Brendan, go ahead. Thank you.
So, you're saying this E times this A equals that B?
Exactly. So E times A supposed to give you B. So you have 1, 0, 0, 0, 0, 1, 0, 1, 0. If you try multiplying that with your 2, 1, 3, -2, 4, 5, 3, 1, 4, it will definitely get you B matrix. And you can try that actually, real quick. 1, 0, 0 means only the first number exists when you multiply here. So 2 times 1 gives you 2. Same thing on the second column when you multiply, only the first number stays, everything else becomes 0. Same thing on the third, only first number stays, everything becomes 0. So it's 3. If you go to the next row, second row, 0, 0, 1, and you apply the same thing, the first two number become 0, only the third one stay. So third one is 3. If you multiply the second one, only the third one stay, which is 1. And if you multiply the third column, only the third one stay, which is 4. And then the last one, only the middle number stays, everything else becomes 0. So when you multiply the first column, only -2 stays, everything else 0. When you multiply the second column, only 4 stays and everything else becomes 0. When you multiply the third column, only middle number 5 stays and everything else becomes 0. So this is our product. And if you compare with B, this is the B matrix. Cool, right?
Thank you.
No problem. Oh, I have one more. Who would like to try the next one? It's not visible directly. Who would like to try C? Any volunteer? Anyone? Okay, then let me pick someone. So I have only 19 did it. Oh man. Oh, now I have a new one. Okay. Elvin, would you like to try C?
So row 3, you just added to row 2.
So row 3 is row 3 plus row 2.
Plus 2 row 2.
2 row 2. Okay, let's see. So row 3 is -2, 3, 1. 2 row 1 is 2, 0, 4. And when you add, we get 0, 3, 5. Exactly what you have on B. So A is 3 by 3 square matrix. The first row is 4, -2, 3. Same thing, B has first row 4, -2, 3. A has second row 1, 0, 2. B also has second row 1, 0, 2. A has third row -2, 3, 1. But B has third row 0, 3, 5. So A and B, they are different only by one row, the third row. And we figured out that the difference between A and B is row 3 plus twice row 2. So we are going to apply the same application on identity matrix. So 1, 0, 0, 0, 1, 0, 0, 0, 1. If you do row 3, which is 0, 0, 1, and you add with 2 row 2, so it's 0, 2, 0, we get 0, 2, 1. So identity matrix, the third row, change into 0, 2, 1. Right? Anything? Yep. So this is our E. Any question? No question? If you don't ask me any question, I'll keep going, okay? Unless you stop me, I don't know where to stop. So I'll keep going. Now, theorem about equivalent conditions for non-singularity. If A is a square matrix, then the following 3 statements are equivalent. If A is a square matrix, then A is non-singular, means AX equals 0, has only trivial solution 0. Means all the xn they have equals 0. And A is also row equivalent to identity matrix. So a square matrix, by combining all 3, we can write a statement like a square matrix is non-singular if if the homogeneous system of equation has only trivial solution and A is row equivalent to the identity matrix. A little corollary about this theorem is that a system X equals B of n linear equations in n unknown means a square matrix. The A is a square matrix, has a unique solution, if and only if A is a non-singular. What does that mean? It means if you try to solve for X from AX equals B, then X equals Y equals Z equals, all these things will have only one single solution, if and only if this A has an inverse. If A has an inverse, then your X, Y, Z, all the variable, they're going to have a unique solution. And if it doesn't have an inverse, then there are two scenarios. Either you have infinite solution or you have no solution. Okay. Now, how do you find the inverse? How do you know whether the system has an inverse or not? We are going to start with the formal method, and then we are going to learn the shortcut method. The formal method of finding inverse is we are going to apply row operation on our A matrix and then turn this A matrix into identity matrix. So we write A matrix on the left, vertical bar, I matrix on the right. And then we're going to apply the three operations, whatever is needed, apply into the entire A, give A and identity matrix. Our goal is to turn the A matrix into the identity matrix. So whatever we need to do, apply those operations, turn your A matrix into identity matrix. If you're able to do that, then whatever you have next to your identity matrix in the result, that's the inverse matrix. If one or more row to the left matrix is 0, then the inverse doesn't exist. Okay. Let's do some example and things will be clear. Our goal is to find A inverse using formal method. So we are going to write A and A identity matrix together. So A vertical bar identity matrix. So we have 3, 2, 5, 3 as our A matrix. And our identity matrix is 1, 0, 0, 1. Our goal is to do some row operation so that eventually this turn into 1, 0, 0, 1. And then we have a bunch of numbers here. So in this scenario, whatever bunch of number you have here, that matrix will be the inverse matrix. And we are going to do the row operation exactly how we applied on row echelon form. So let's do one by one. Our goal is to get to the turn 3 into 1. This is what we want first. Turn 3 into 1. So there are few ways of doing it. One, you can divide by 3. If you do divide by 3, then you have to work with fraction. So if you're okay with fraction, no problem, go ahead, divide by 3. And if you don't like fraction, then we can do row 1. So make sure I write this one. Row 1 is row 1 minus row 2. If you subtract row 2 from row 1, the 3 will turn into 1. And then we don't have to work with fraction. So let me go with this operation. So 3 minus 2 gives us 1, 5 minus 3 gives us 2, and then I have 1 minus 0, which is 1, 0 minus 1 is negative 1. And then let's keep 2, 3 for now. We want to, yeah, we can keep 2, 3. So at least one number is satisfied. We got the first numbers. Next, we want to convert this 2 into 0. So who can tell me the row operation we can apply to convert our row 2 into Brendan?
We could do like 2R1 minus R2.
2R1. So R2 minus 2R1. Whatever you're changing, you should keep that and then change the other one. Okay, let's see. R2 is 2, 3, 0, 1. 2R1 is 2 times 1, 2. 2 times 2, 4. 2 times 1, 2. 2 times negative 1, negative 2. And when you subtract, all the sign will change. So the result will give us 0, negative 1, negative 2, and 3. So we have 1, 2, 1, negative 1, 0, negative 1, negative 2, 3. Okay. Now this one is satisfied with this one. So you're happy. So we are going to go for the next one. This -1 would, sorry. This -1, we want to turn this into +1. So it's the easy one, right? All I need to do is change the R2, not change, divide the R2 by -1 or multiply by -1. So -1 R2. So we got 1, 2, 1, -1, 0, 1, 2, 2, -3. We are very close. So the third one is also satisfied. We have 1, 0, 1, and we have 1, 0, 1. So all three we got it. Now the last one we need to change is these two. So we are going to change R1. Who can tell me how can you change the 2 in the R1 into 0? Which row operation is supposed to apply? Ashif.
1 minus 2 R2.
1 minus row 1 minus 2. 1 minus 2 row 2. Perfect. So if you want to see the row operation, we have 1, 2, 1, -1, and 2 row 2 is 0, 2, 4, -3. When you're subtracting, all the sign will change. So we get 1 minus 0, 1, 0, -3, and +2. So we have 1, 0, -3, 2, 0, 1, 2, -3. And if you observe, see, 1, 0, 0, 1 is the identity matrix. So you got the left side as identity. That means whatever you have here, that is your inverse matrix. So your A is 3, 5, 2, 3, row wise 2 by 2. And we just found out that its inverse is also 2 by 2 matrix. It's -3, 2, 2, -3. I did something wrong, right? I feel like I did something wrong. Let me check. 5, we swap 2 and 5, and I change the sign. Yeah, this should be 5, but this one should be 5. Oh no, the bottom one should be 5. So why did I make a mistake? The 0, -1, -2. And did I make mistake anywhere in any step? So this one should be 5, as far as I know. This should be 5. So I made a mistake. So the first one is row 1 minus row 2. So 3 minus 2 is 1. 5 minus 3 is 2. 1 minus 0 is 1. 0 minus 1 is -1. The first one is correct. Next, we multiply the row 2. Sorry, row 1 by 2. So -2, -4, -2, +2. And we have 2, 3, 0, 1. So -1, -2, 3. So 1, 2, 1, -1, 0, -1, -2, 3. Now -1, I just need to multiply or divide by negative. So 0, 1, 2, -3, 1, 2, 1, -1. And then R1, which is 1, 2, 1, -1, and it's subtracting twice row 2. So 0, -2, -4, +3. So 1, 0, -3, and 2. 1, 0, -3, and 2. Looks right. Then how come I have 2 here? Do any of you see any mistake in any of the operation we did? 1, 0, 0, 1. We have right identity matrix. So we have 3 times 3, 9. 9 minus 5 times 2, 10. 9 minus 2 is -1. 3 times 3 is 9. 5 times 3 is 10. So 9 minus 10 is -1. This swapped 3 and 5. 6, 5, and 2. Yeah. Somewhere I made a mistake. This one should be 5. But for some reason I have 2. But again, let me check in case if I know it wrong. Inverse, not in, yeah. Inverse, it's 2. But I feel like it should be 5. Inverse matrix calculator. Calculator. I don't have the answer. So I just want to make sure that I got the correct one. 3, 5. So we have 3, 5, 3, 5, 2, 3. This one is 2, this one is 3. Calculate. Oh yeah, we can actually check that. Good. I didn't realize that. Okay, see, that it draw operation. See, I was correct. It should be 5. So ChatGPT sucks. Oh, so that 5 should be 2. So what they did here? They divided by, so they worked with fraction, okay. And then they did exact same operations. The only difference is that they divided by 3 instead of subtracting. Okay, so it's 2, 5. 2, 5. Come on, oh, okay. So 2 is here, 5 is there. No, it doesn't look right because we have to swap the 2 places. How come they didn't swap the 2 places? Yeah, let's multiply them and see whether we have I. So they said 2 is here, 5 is there. Is it true? 2 is here, 5 is there. No. Okay, let's multiply real quick. 3, 2, 5, 3. And we got what? -3, 2, 2, -3. I'm pretty sure this is wrong because we're supposed to have the same 2 numbers, but in reverse position. So if you multiply 3 times -3 is -9 plus 10, which is 1. And then okay. And then the second one, 3 times 2 is 6 minus 3 times 5 is 15, which is -9. So see, we're supposed to get 0, but we didn't get 0. That means this is wrong. So this one is 5, really? 3 times 5 is 15 minus 3 times 5 is 15. So we get 15 minus 15, 0. Oh man. And then we have 2 times 2 is 4 plus 3 times 3 is 9. No, what I'm doing. 2 times 3 is 6. And then 3 times 2 is 6. Minus 6 plus 6, we have 0. And then 2 times 5 is 10. Minus 3 times 3 is 9, we have 1. So yeah, it should be 2, 5. Oh. In the final step, -1 plus 6. Alvin, which step you're talking about? Finding the I or checking that whether it gives us the I? Or R1, 2, R2. R1 minus 2, R2. Okay. So R1, 1, 2, 1, -1. Oh, yeah. 2 times 2, 4. 2 times 3 should be 6. Oh, man. Thank you so much for catching that. So this is -5. No, sorry, +5 because our 6 is positive. So 1, 0, -3, 5. Wow, now it's correct. But you may wonder, how do I know whether I am wrong, right? Like I could have just accepted my answer. The thing is that there is another way we can find inverse easily for 2 by 2 matrix. I'm going to show you now, but this works only for 2 by 2 matrix, not for 3 by 3. So there is another method which we are going to learn details later. But for now, for any 2 by 2 matrix, there is another way we can find inverse. It's called using the determinant. Determinant of a matrix, a 2 by 2 matrix. So if you have a matrix A, B, C, D, then its determinant is AD minus BC. So it's the difference of their diagonals. And you always have to take the left to right diagonal first and subtract, downward diagonal minus upward diagonal. So AD minus BC. And then the inverse of the matrix, you do 1 over AD minus BC, means 1 over the determinant of the matrix. And then you are going to change the sign for A and D. And you're supposed to swap the places B and C. But for some reason, they didn't swap, right? 3, 5, 2, -3. So yeah. Or you swap A and D and then change the sign. Oh, the other way around. Okay. So B and C, you have to change their signs. And D and A, they swap their places. So these two swap places and these two change their sign. And that's it. This is your inverse. So in our case, I was so sure that I did something wrong because I did all of this mentally. We have A equals 3, 5, 2, 3. That means our determinant was 3 times 3, 9, minus 5 times 2, 10. So it's -1. Now the inverse should be 1 over -1, which is -1. And then we are going to swap places, 3 and 3, which is the same. It doesn't do anything. And we have, so we are going to, yeah. Wait. 3 times 3, 9, minus 10, -1. So -5 divided by, so -5, -2 here. And 3 and 3, they go here. So 3 and 3, even though we swiped the places, but we still have the same numbers. And 5 and 2, we have to change their sign. So since both 5 and 2 are positive, when you change the sign, we get negative. And then you multiply. So when you multiply by a constant, it means you're multiplying every element by the constant. So we get -3, +5, +2, -3 on the second row. The first row from 3/5 turns into -3/5. The second row from 2/3 turns into 2 -3. And that's how I knew that I'm supposed to have 5 in my inverse. I cannot have double 2. Any question? Did I lost you guys? Who is lost? Is there anyone who is very lost and have no idea what we are doing? No? Then let's try 1 3/3. For 3/3, we cannot use this method of determinant. 3/3 determinant is hard, so we are going to use row echelon form. So you start by AI and convert into I A inverse. So we have row wise 1 0 1 3 3 4 2 2 3. That means we have to use 3/3 identity matrix. 1 0 0 0 1 0 0 0 1. And our goal is to convert this into 1 0 0 0 1 0 0 0 0 0 1. And then we have a bunch of numbers. So that will give us the inverse when you have your identity matrix on the left. So right now we are lucky. Our first position is already given 1, and what we wanted was also 1. So we don't have to do anything for the first position. Then we go for the second position. Our second position is 3. We want this 3 to turn into 0. We want to make 3 into 0. Ashif, go ahead.
So equals R2 minus 3R1.
Perfect. 3R1. So if you want to see, we have 3 3 4 0 1 0, and 3 times R1, which is 3 0 3 3 0 0. Changing the sign will change everything. So we got 0 3 1 -3 1 0. So 1 0 1 1 0 0, they're same. Then we have 0 3 1 -3 1 0, right? 0 minus 3 is -3, then we have 1. And we can also change R2 at the same time. So R3. So a new R3 is old R3, and you can apply the same rule, twice R1. So the math, current R3 is 2 2 3 0 0 1. When you multiply R1 by 2, we get 2 0 2 2 0 0. And when you subtract, all the sign change. So we got 0 2, 1, negative 2, 0, 1. So 0, 2, 1, negative 2, 0, 1. And we are very happy because the first entire column is same as the identity matrix. So we go and do the next one. We can change 3 or you can change 2. We can do this one by one. So again, I don't want to work with fraction. If you don't want to work with fraction, that means our R2 is R2 minus R3. We're just subtracting third row from the second row. Then we have 3 minus 2, 1. So we get 1, 0, 1, and then 1, 0, 0. Then when you subtract the third row from the second row, we get 0 minus 0 is 0, 3 minus 2 is 1, 1 minus 1 is 0, negative 3 minus negative 2. So negative 3 minus negative 2 means negative 3 plus 2. So we have negative 1 here. 1 minus 0 is 1, 0 minus 1 is negative 1. And we have 0, 2, 1, negative 2, 0, 1. So I did not change the third row at the same time because we can easily use the second row to get to the third row. So new third row. Our goal is to convert these 2 into 0. So what can I do? Any idea? We can get the help from row 2. So R3 minus 2 row 2. So R3 is 0, 2, 1, negative 2, 0, 1. And 2 row 2 is 0, 2, 0, negative 2, 2, what, negative, what, 0, 2, 0. And then negative, I should write 1 below another, 0, negative 2, 2, negative 2. All the sign will change when we subtract. So we get 0, 0, 1, 0, negative 2, and 2 plus 1 is 3. So 0, 1, 0, 1, 0, 0, 0, 1, 0, negative 1, 1, negative 1. And the last line is 0, 0, 1. Oh, 1, 0, 1. The last line 0, 0, 1. Then we have 0, negative 2, 3. And if you observe, this is identity matrix. That means whatever we have, unless I made any type of mistake, then this is our inverse matrix. So A inverse is 1, 0, 0, negative 1, negative 1, 1, negative 1, 0, negative 2, 3. I hope this is correct. Any question? So basically all I did was use reduced rational form on our matrix to reduce our matrix into identity matrix. And we got the inverse matrix. So you may wonder, like, if there exists other easy method, why we are using this method? Well, we are using this method because not every matrix has an inverse. So you may not always find inverse to solve for your matrix, solve for a variable. So when you don't have an inverse matrix, this is the way you can find the solution for your matrix. So that's why you need to know this method. So, oh, I have the answer for this one. Cool. So let me put this here. And let me check. 1, -1, 0. Oh man, I made a mistake again. This should be 2 and -3. So where did I make the mistake? 1, 0, 1, 1, 0, 0.
Professor,
Huh?
how did this one
Oh,
is
I'm not
zero?
done because I still have this one. Yeah, that's why. Oops. Sorry about that. I'm missing one more row operation. So to get rid of this one, yeah, it's R1 minus R3. That's why. So R1 minus R3 gonna give us 0 minus -2 is 2 here. 0 minus 3 is -3 here. Good thing I have the answer. So we have 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 2, -3, -1, -1, -1, 0, -2, 3. So this is the inverse, not here. And this is the identity matrix. Okay, let's see what you're going to do next. We're going to solve using inverse matrix. We're going to solve system of equations. Oh, and then I have triangular matrices. Okay. Yeah, so most likely in our next class, we will be able to finish this. Also, Monday, we don't have any class. So we are going to have it off on Monday, and we are going to meet instead of Monday on Tuesday. Tuesday follows a Monday schedule. However, I have my own class also. So I cannot be at Hunter in person. So we'll have another online class on Tuesday. And then we are going to meet in person next week, Wednesday. So 2 online class and then 1 in-person class. And I'm to return your exam on Wednesday. Okay. Any question?
So we have class on both Tuesday and Wednesday, or
Exactly.
okay.
Tuesday and Wednesday.
Okay, thank you.
Any other question? No. Okay, then. Thank you so much for being here. We are going to meet again online on Tuesday. So have a good Friday or not Friday, Saturday, Sunday, Monday. 4 days off. Have a good 4 days weekend.
A good weekend,
And I'm going to post the homework, but there won't be any homework next week. I'm going to give you the homework once you're done with 1.5. So goodbye, everyone. Enjoy your weekend, 4 days weekend. And if you want to, can you post extra credit? I can do that. Maybe I can assign few required question and few extra credit question. Yeah. Okay. Bye, everyone. See you again next week, next Tuesday.
Bye-bye.
Bye.